presentation with the second lecture of the Shan, continue from the yesterday's spectroscopy and 2D materials.
Okay, you can hear me well in the back? Okay, so what I decided to do today is to give you kind of an overview of what experimentally the community has been able to achieve, in the past few years by studying this new platform of materials. And, I don't have a strict agenda. So if you want to discuss certain topics more in depth, I'll be happy to. So I don't need to finish my slides. Okay. So I think Alan has already discussed quite a lot about moraine materials. So I just want to show you some experimental data. So there are two different ways to make moraine materials. So one is to use, same material, same monolayer, and then you cut into half and pick one up and put on the other one by controlling the relative twist angle. So that's one way. Or you can have two different lattices, and they have lattice mismatch. You can put them on top of each other by doing second harmonic generation. You know the crystallographic axis already for each, and then you bring them together. And you can add twist angle or just well aligned. So the moraine lattice depends on twist angle. So this is relative to the lattice constant of each lattice. So you can see that, if you use heterobilayer, two different materials, the lattice constant is determined pretty much by the lattice mismatch. And then it has a relatively weak dependence on the twist angle. So this is good in the sense that if you want to get something homogeneous, because the lattice constant is mostly determined by the lattice constant mismatch, right? But you are pretty much limited by how large the moraine period you can achieve. On the other hand, if you use same material with the angle, you can tune the moraine lattice to a very large number. But on the other hand, because we work with materials, there'll be some disorder in terms of twist angle. So you get patches, somewhere you have a large lattice constant in terms of moraine, you have a smaller. So this is more challenging if you want to study small twist angle samples. So that's the limitation in experiment. And that's something experimentalists try very hard to overcome, but still a big challenge. So on this picture, by the way, this is now PowerPoint. So this is a real image. So this is what you can see if you shoot electron beam and look at the scattering, diffraction. And we put together. And because the process is dependent on the atomic Z number, so you will be able to identify which element you are looking at. So the small dots here are individual atoms. And if you look back a little bit, you also see on top of that, you have this moraine pattern, right? And because each of those lattices are hexagonal, and you put them together, you get this triangular moraine superlattice. Okay, so so this moraine material introduces this new length scale. It's somewhere between the real atomic crystal and the cold atom optical lattices. And this new length scale actually gives us, a new platform to pursue different physical phenomena. So
I have a quick question from this. You said there was a picture in the middle one.
Yeah.
What does color stand for?
Color is by hand.
Oh, color. Oh.
Color is by hand.
But
yeah.
That's taken by
TM.
So
Yeah.
So like the color is by hand, but then there must be some dark and bright.
Yeah,
So
the interest.
What that representing? Is that the electron density or?
So those are the high symmetry stacking orders, so this could be metal sitting on top of metal. So you have a large, let's say Z number. So you have a higher intensity. So this is how we do it. So I should have included a scale bar. This color corresponds to this intensity. This color corresponds to that intensity. So this is mostly
Electron
Z
Z
now.
Got it.
Yeah. In some nonlinear fashion, yes.
There are 3 kinds of.
Yeah. Oh no. So there's so this spot, the cartoon ones may be better. So you can have metal on top of metal, and the chalcogen on top of metal, and the metal on top of a chalcogen. So this and that, they are different. And this is the same. Okay, so this field is relatively young, and I think if not all of you, probably most of you have seen this. Alan probably showed this. Started when the MIT group demonstrated superconductivity and the correlated insulating state when they put 2 monolayer graphene on top of each other with twist angle about 1.1 degree. Okay, and this pretty much just opened the whole field. And now we can stack not just the graphene, graphene on boron nitride and some other semiconductor monolayer on semiconductor, so on and so forth. And it's quite, amazing that, within a period of less than 10 years, we've been able to observe pretty much, every correlated or topological phenomena people have seen in other materials, in 3D materials. And what's more exciting is that, there are a few new phenomena that, maybe you guys have dreamed about, but not realized experimentally. And those effects in blue have been observed experimentally using this Moray platform. So if I have time, I will talk about this. Okay, so this is a plan. So I will just summarize, the general features from this emerging new length scale on the Moray period. And I'll focus on a particular class of material. This is a transition metal dichalcogenide. It's mostly semiconductor. And then I would like to talk about the correlation effects from the flat bands, so mostly Hubble physics. And then if I have time, I want to talk about this topological effects from this flat term bands. And this is beyond, the K-Malay model, more than that. Okay. So Alan probably already emphasized a lot that, if you have semi-metals or semiconductors and you form Moray, in that case, if you look at the structure carefully, when you twist only at some specific angles, this is strictly a crystal. But for any arbitrary angle, actually, this is some kind of quasi-crystal. So it's strictly atomic level. It's not periodic. But if, the Moray period is much bigger than the atomic length scale, and we are talking about the semiconductors or semi-metals, their states sort of confined in some momentum space. In that case, the low energy physics, the electrons will see the structure as periodic. And in that case, you can use Bloch theorem and you can analyze those bands and can talk about Moray mini bands. So that's pretty much just, the zone folding, how to get the Moray mini bands. And you probably have already heard from Alan. So that's kind of the first important properties. So next, the important properties, of course, I don't need to mention, strong correlation because now the bands are flat, right? So just to give you a number, for real materials, this ratio of kinetic energy to Coulomb interaction energy, which is proportional to the effective mass and the period, typically is on the order of 0.1 for lattice on the order of nanometer. But for Moray material, because now we are talking about 10 nanometer period, and this ratio can be very big, bigger than 1, I mean. So this is already into the strong correlation regime. So you may wonder, why this 10 nanometer is such a magic number. We always talk about this, right? So if you just look at this, the larger periods, the stronger correlation, why don't you make it 100 nanometer or even bigger, right? So in experiment, there's a limitation. So let's say your material has some disorder, right? If the disorder density is very high, the average distance, let's say, is something smaller than this 10 nanometer, you already destroy this, coherence. So this doesn't work anymore. So 10 nanometer thing kind of a convenient because, we can get the disorder density down that, for a few lattice sites, you don't have any disorder defects, but still, 10 nanometer is large enough for us to see strong correlation. Okay. So this is the length scale we'll be working with. And then, of course, this very attractive feature of this material is like highly tunable, controllable. So you can make a Moray pretty much with arbitrary composition because of the van der Waals interaction, right? So you don't need to worry too much about putting different materials together. This twisted angle can be controlled. In early days, what we do, like for each device, you fix the twist angle, or if you have inhomogeneity, you search around your sample here and there, you pretty much have different twist angles. But with the new development of a quantum twisting microscope, now we can continuously tune the relative twist angle between the layers. So this idea is relatively simple. You have one layer sitting on your substrate, another layer you put on a AFM tip, and then you put them together. But what's kind of surprising that even when they stick together, you can still rotate, the bottom layer, for example. And it works surprisingly well, even when you push your AFM tip very hard. So under some high pressure, it still works. So this is a new development, and more results will come out, when we can precisely control the twist angle continuously. Yes.
When you use AFM tip, how uniform is the twist angle across the entire sample? It's
a small, so the sample size on the tip, it's much smaller than micron. It can be quite uniform. And then you experiment, we can also sort of massage them, so you make them uniform. So the other advantage is gate tuning. I already touched upon this quite a lot yesterday. So basically, it's some kind of a parallel plate capacitor structure. So in this case, I just have two gates, top gate and a bottom gates. And with those two voltages, you can change the doping density. And because, the Moray density is small compared to atomic density, it's about 1,000th. So this capacitor-like structure can actually introduce a lot of doping density. So you can sweep through many bands. And this is a kind of very interesting point because, in chemistry, if you fill one shell, like if you add one, you change to a different element. So basically this is doing is like you sweep through, you change the character significantly. And so with those two gates, the other thing you change is the displacement field. I gave an example yesterday for this optically detected resistance and capacitance. In that case, the property is not very dependent on the displacement field. But in other example I showed, when the two layers are the same, homobilayer, you change the potential difference between the two layers, physics can change very significantly. And this can be also in situ controlled in a continuous fashion. So I just want to show you, this continuous tuning sweeping through multiple Moray minibands, and also get back to some of the questions yesterday about the compressibility measurements. So I mentioned that there's optically detected technique to measure local electron compressibility. And there's another way to do this, which is just doing the capacitor measurement. So in the scheme, for example, I have my sample here. I have my top gate. I can apply some DC voltage on my top gate. But on top of that, I'm going to add an oscillating small AC voltage to my sample and try to see what is the current charge density collected or induced by this AC voltage. So if you look at this ratio, you are just looking at, for this much energy change, how many density you are going to induce, right? So this basically is measuring density of states. So here's some example from this paper, for this heterobilayer combination. And this capacitor normalized by the geometrical value, So if there's no interaction, you expect this to be flat 1, the geometrical value, right? But then you see dips on top of this baseline. And then this dip like a 1, 2, 3, 4, up to 4 charge per Moray unit cell. And because each band is spin and valley degenerate, so that means we cover two bands. And I'm not showing data. We can keep going, actually. You can see 3 or 4 bands. So yesterday, there's a question about this background, right? So this background, you see again in this capacitance measurement. And, so the way to think about this is we have 2 length scales. One is the average distance between charges, for particular doping density. The other one is, I'm putting my sample very close, some distance away from my top electrodes. And for small density, you always get into the regime when the separation between the charge actually is bigger than the separation from your sample to your metallic top gate, right? And in that case, you have to think about the effect of image charge. So at low density, you don't just have charge in your sample, you have image. It's like an exciton. So this interaction actually will change a lot. And that's, the major contribution of this background. But for experimentalists, the question is, how do I extract the information about, for example, the chemical potential drop of each particular states. So this background is an problem. So you need to model this, understand this background a little bit better in order to extract information. So there's always some kind of error bar, plus minus, right? So if I want to know this area, where do I cut as my baseline? Okay.
That HBM layer in between is like their
Dielectric, yeah.
But their thickness is like chosen, or is also more
Yeah. So we can choose whatever thickness we want to use. So for example, this affected this background, so in this case, this D distance is about 2 times of the Moray distance. But if I make this D larger, then the background will be smaller. If you make a D smaller, then the background will be bigger. Yes. Oh, okay. So what I'm saying is, so the capacitance you measure, at a very large doping density, it will just go to the geometrical capacitance, right? And then, but you see that, if I ignore the dips due to the insulating states, when Fermi level is inside the gap, you see this goes up, right? So this can be well above 1. And this is something, is due to interaction. Yeah.
Background picture that you can.
Oh, so this background happens at the very low density, right? Then in that case, interaction is important. High density, we don't need to worry about background. It's 1, right? So in some sense, your sample is part of the device. What you are measuring is not just the chemical potential of the sample alone. So the top gate is part of it. Okay, yeah.
Activity is somehow if I think of it as a capacitor, this the capacitance decrease.
No. So this capacitor is bigger than 1. More than this, yeah. Yeah.
This may be jumping ahead.
Yeah.
But in these new quantum anomalous Hall measurements, there's a lot of like residual resistance.
Yeah.
At quantum where the Hall resistance should be going to 0.
Yeah.
Do people think that this could be coming from like what you call like the image charge?
No, mostly those are due to the sample cleanness disorder in the case you are mentioning. Yeah. Okay, and then the last point I want to bring up is the simplicity. I give you an example of this quantum physics. So this is kind of, band structure of a typical representative, atomic quantum lattice. And what we care about is some kind of flat bands, which describe localized magnetic moments, and some itinerary electrons, that's the dispersive bands near the Fermi level. But in real material, this is what you usually get. It's a spectrum. And you can write down Hamiltonian, for those 2 ingredients and introduce some coupling between them, and and you can solve the problem, although with a lot of challenges we heard. But whether this can be directly compared to experiment is a question mark, because you see this, there are many other things around can mess up, right? So this idea of quantum simulation is to find kind of a simpler system that's described by the same Hamiltonian, and it's very controllable, and use this as kind of the analog system to study the Hamiltonian. So this quantum lattice actually has also been realized using this Moray material. And the idea here is that if I have one sheet, in this mode insulating state. Then you can think about the charge in the mode insulating state as localized spin. And then I can have itinerary electron in the other layer of the moire. And this, if the moire potential is weaker in that layer, it will have more dispersive energy bands, and that can be your itinerary electrons, and they talk to each other. So this way, we can have the two important ingredients for Kondo lattice and use this to explore the Kondo lattice problem. And if you want to find more, you can look up this paper and some follow-up studies. Okay, so if no questions, I will get to the materials of interest of today. So I will be focusing on this class of material, transition metal dichocogenites, and they are semiconductors. Those are the ones I listed here. And some are edge stacked, so that means, one layer is like this, and another layer is 180 degrees rotated, and so on and so forth. So they have been very widely studied and easy to exfoliate and easy to get cleaner samples, so this is kind of the choice of our experiments. So if you look at their structure, so in the middle, you have metal, your moly or tungsten, and top and the bottom, you have the chalcogen atoms. So if you look down from top, it's just like a boron nitride. So the A and the B sublattices are occupied by different elements, so one is a metal, the other one is two chalcogen atoms on top of each other. So the electronic band structure in the limit monolayer just behaves like what you would imagine, because this is like graphene, right? But now you break the AB sublattice symmetry, so you'll get a gapped graphene. So here it looks like gapped graphene. So there's a large gap. And this is on the order of 1 to 2 electron volts, depending on which compound you choose. The other ingredient that graphene doesn't have is the very large spin orbital interaction. And this is because we have a very heavy metal in this case, unlike carbon in graphene. So this strong spin orbit coupling actually breaks the spin degeneracy of each band. And this splitting can be very big, on the order of a few hundred millielectron volts. But this material itself has a time reversal symmetry. So that means, from the K point of the beryllium zone to the K prime or minus K point, the spin has to flip to preserve time reversal symmetry. So this material has this double degeneracy, spin and the valley are coupled. So this is different from graphene. So there you have fourfold degeneracy. So here is just double. And the symmetry is such that, the spins, we're talking about Ising spin, they're out of plane. So SZ is a good quantum number. And if you, because you can estimate how large this out of plane effective magnetic field is, you can split this by hundreds of millieV, and this corresponds to something like 1,000 Tesla. So kind of one consequence is that, if you apply a in-plane magnetic field, nothing will change pretty much for a monolayer material. Okay, so now we're going to stack them together. So in this example, we put two different monolayers together. And because of the lattice mismatch, for angle aligned, this period is about 8 nanometer. And Alan had an earlier paper. So for example, for this pair, I don't know, he probably studied different pair, but the idea is the same. So those two materials, the band edges, they don't align. So for in this case, if we are interested in the valence band, this will be simpler because the spin split bands is like a few hundred millieV away. So we can forget about the spin split bands. And one of the compound, tungsten sulfide, for example, the valence band is also very deep. And then what's important here, if I just put a little bit of a whole doping, so those are the important bands. And in this case, you can see those bands are pretty much isolated from the rest, right? So if I look at the single band, for example, the top most valence band, in this case, it's isolated from the rest. This, of course, is an approximation, right? So if you have an isolated band, this problem can be projected to, triangular lattice Hubbard model. So we can write down Hamiltonian such that, we just have two terms. One is hopping between the nearest neighbor sites with this hopping amplitude T. And then you have on-site Coulomb interaction. And this, of course, is approximation. And for this system, T is on the order of 1 to 10 nanometer, depending on twist angle. If you make the lattice smaller, then your T is going to be bigger, right? Yes. Oh, I'm going to. Yeah. So this is a first step. And how large this U is, we can just estimate from the size of a 1 year orbital. And in this case, about 2 nanometers. So that means, on-site Coulomb interaction is on the order of 100 millieV. And this 2 nanometer has also been verified by STM measurements. So you see how large the 1 year orbital is. So this is an earlier experiment. So what we measure is resistance as a function of hole filling factor. So one means, 1 hole per Moray unit cell. And I told you those are doubly degenerate, spin value are locked. If you cool it down, the resistance shoots up. So this is an insulator. And at 2, filling equal to 2, the resistance also shoots up when you lower the temperature. So, for very early measurements, I mentioned about the difficulties to achieve ohmic contacts. And here you see the problem, when I make the doping density very low, resistance shoots up. And this is coming from the contacts. It's not the sample properties. And whether there's anything interesting here, we cannot observe. Yeah.
How do we know that? So that lattice filling factor is controlled by gate voltage?
Yes.
How do we put that as 1 and 2? I mean,
yeah, that's an excellent question. Okay, so those the lattice filling factors actually it's so let me explain the way we determine this. Okay, your capacitance, from the thickness of your HBN. So if you apply certain voltage, the density you induce in the system. So that's kind of one way to sort of estimate the carrier density. If your sample is good enough, we can see quantum oscillations. Then you can look at the Landau levels, and then from there you can precisely calibrate, the density. So we know the density. We can know the density very well, right? And then in order to know the filling factor, you also need to know the Moray density, right? So from experimental point of view, we roughly know the twist angle for the heterobilayer, it doesn't change much. From there, you can roughly determine where the filling 1 is going to be and the filling 2 is going to be. And then in that case, you can determine the rest. But this is not very precise. The more insulating states you have, the more references you have. Yeah. Yeah.
One of the capacitors.
Yeah.
How do you?
Yeah. Yeah. So this is a good point. So for large filling factors, their contribution is very small. You already saw in the capacitance measurement, when you have higher fillings, the baseline is 1. So
this particular data is like just only control the
Con-
gate voltage, or like in the some certain field zone,
Yeah.
magnetic field zone?
no magnetic field in this case. So in this case, the device structure is just as what I showed here. We have top gate and a bottom gate, and we vary those two together. So so let's say if those two gates are symmetric, you have symmetric part and anti-symmetrical part. So symmetrical part, it's just the average of the two gate voltages give you the change in density, and anti-symmetrical part give you the vertical displacement field. We can vary those two gate voltages in the right combination just to change one of them. Or we can map out, the two axes, and then if we know the thickness, we can convert them to displacement field and the filling factor. Okay. Yeah, so in the experiments, there are a lot of knobs to control. Yeah, so from this experiment, we can tell that there's an insulating state at half filled band and the full filled band. Okay. Yeah.
So why does the contact resistance go so?
Oh, okay. Yeah, so this is an experimental question, right? So if you say, I want to put contact on this piece of wood, you're going to get a huge Schottky barrier, right? So this is why the contact resistance goes up like crazy, right? But if I put doping, if it's some kind of metal, so I put a metal, you get a very good contact, right? So always the contact resistance strongly depend on the doping density of your material, right? And this actually is the key to achieve good contacts, and that's the approach we use to reduce contact resistance. So let me just digress, say a few words. So the current design is, we make the sample into, let's say, 2 different regions. One is with like low doping density, something you can control, but the part that you put the metal gates on, you heavily dope that side. So that way you can achieve good, metal to semiconductor contact. And then from heavily doped to lightly doped part, you have relatively small,
How do you spatially modulate the?
Oh, with all those gates, So I just show you those 2 gates, but in experiment, you can have many. Yeah. And by the way, this is also the technology people figure out, in your computer, for silicon, people work on the contacts for decades in order to achieve, low Schottky barrier, no Schottky barrier contacts. So the same philosophy. So the question is, what could be the state, right? It's this. If you think it's a Hubble model, then some kind of a Mott insulator will be a good candidate for this. So that's kind of a picture when you have a large interaction, you can have Coulomb gap opening. So another piece of experiment that supports this picture is that, in a Mott insulating case, once the charges are localized, you still have the spin left. So there'll be interesting magnetic interactions. So we measured the magnetic susceptibility as a function of the temperature. Those are the dots. And this susceptibility as a function of temperature follows pretty well Curie-Weiss law. And then, you can estimate what this Curie-Weiss temperature is from this fit. So this actually determines the J, the super exchange interaction between the localized moments. And from this experiment, we got the Curie-Weiss temperature to be on the order of 1 Kelvin. And in a super exchange picture, it's proportional to T squared over U. Yeah.
I thought your bands were spin polarized.
Okay, but we have two values, K and K prime. So they are, yeah, so you have both. Yeah. Yeah.
How do you measure this is like magnetic susceptibility
Yeah.
of the two single
Yeah,
layers
yeah.
put together
Yeah.
more, right?
Yeah.
So
How do you measure this?
how do you
Okay,
measure
yeah. So let me do this here. I don't have slides. So I showed you the band structure of this material, right? So we have K point and a K prime point. And let's just ignore the spin split bands. So let's say this is a spin up, but this is spin down, right? This is kind of the difficult measurements because we are talking about at filling equal to 1, the spins are 8 nanometers away from each other. So in an entire sample, of micron square size, we have on the order of 10,000 spins. So how do you measure susceptibility of 10,000 spins, which are embedded in many other spins? You have boron nitride, you have graphene, this and that. And you also have a silicon substrate. And this is done using optical technique. I didn't get into this yesterday, but so this is energy. So in this particular material, what happens is that so those bands are coming from certain orbitals, for example, moly sulfide, moly telluride, whatever, this TMDs. So there's a selection rule, a very good selection rule that the K point and the K prime point optical absorption, this works for left-handed and this works for right-handed excitation. So this is a very good optical selection rule, and it works very well actually for a relatively large momentum space. Okay, and this certainly work if you just look at mini bands, a very small momentum space. So we use this property. So let's say we want to measure the magnetic susceptibility, right? If I don't apply any magnetic field, I told you this material has time reversal symmetry, right? So if I measure the difference between left-handed and right-handed light absorption, I should get 0. Right. So, and this is called MCD. So we just look at the difference between left-handed, right-handed, and let's normalize it. So let's say this is the reflective intensity of the right-handed, left-handed, the difference, right? So this is 0 when magnetic field is 0 because you have time reversal symmetry. But now I'm going to apply a very small magnetic field to measure the susceptibility, right? So in that case, the two K and the K prime value will be tilted because we apply out-of-plane magnetic field. I mentioned that there's no response to the in-plane magnetic field because of the Ising spin. But if you apply out-of-plane magnetic field, so one will be shifted down a little bit, the other one will be up. So in that case, if you have a Fermi level at a certain level, so in the extreme case, you can quench one handedness and leave the other handedness intact, right? But if I just apply a small magnetic field, so this thing is not going to be zero when magnetic field is not zero. And what this quantity sort of represents will be the imbalance between the K and the K prime values. And because the spin is locked to the valley, so this difference is proportional, not just the valley polarization, but also spin polarization. And that's just the magnetization. So this MCD is linearly proportional to the magnetization. And the ratio to the small magnetic field will be just the susceptibility. So this is how we measure it. Yes. What is the? Oh, very small, you know. Well, 100 millitesla, Tesla. Okay, so yeah. Yeah, so yeah, so what is the magnetization as a function of B field, right? So this is the question. So for small magnetic field, it's right, and then it will saturate.
It's like something that people are interested in.
Yeah. So you know, you can this has been well studied, you know, so you can fully spin polarize in this case. Yeah. And you know, due to interaction, you can get a large G factor, you know, so all those have been studied carefully before this. Yeah. Yeah. So this technique is not sensitive to the in-plane magnetization because we come in with normal incidence. So you don't, you can't measure that, unfortunately, using this technique.
Measurement, does it just become zero?
We don't see it if it's strictly like this. Okay, so so this is just a cartoonish picture. You know, like those arrows, what does it really mean? It's so you know, on that we have Ising spin, right? So what are those arrows mean? So I just put there. I don't mean that the spin will line like this. So, okay, so this is the measurement. So the question is, you know, what is the ground state of, what is the magnetic ground state of this insulating state we observed? And, you know, from this measurement, it tells us we have local moments, but there is no ordering. We don't see ordering at this temperature. And this is down to 1.6 Kelvin. So I put a question mark, you know, is this some kind of what people usually say 120-degree near order antiferromagnetic insulator, or it's something else. So this requires a little bit more maybe theoretical studies. Yeah. Current system is 1.6 Kelvin. Yeah, it's very.
So in order to ensure that the signal, MCD signal from that twisted layer,
Yeah.
other than other C.
Yeah.
So that means, so I mean, of course, you know, moly disulfide or tungsten disulfide has this kind of property, but we know that, you know, like for example, might have a little farther down below level maybe have this kind of property. I mean, anything have this type of any imbalance between the tradition of the selection rule can give this one.
Yes. Yes. Yeah, so this is a very good point, you know. So one advantage of optical measurements is the selectivity. So you can tune the light color to match the resonance in particular material. So in this case, we tune the color to match the exciton resonance in a particular layer. So, and if you look at the response at some other frequencies, you don't get this. Yeah. And this also makes the signal strong, because it hits the resonance.
We might have it as good. That's why.
Yeah.
But you said that in the in plane it does not matter. So
In plane because it doesn't, because of this large Ising spin.
your revised rate showing the anti-ferromagnetic order.
No order, maybe interaction, I will call it.
Sure, but
Yeah.
I'm thinking like, is that a finite Q order, and is the MCQ like able to measure like ordering not at Q0 but finite Q?
No, that's not
yeah.
ordering, right?
Yeah.
Your Curie Weiss law is higher than ordering temperature.
Yeah.
Kind of interaction.
Yeah.
But still, that's a separability. Is like divergent at finite Q? That's the question. Like, is that like MCQ technique like to resolve?
No. This is a very rough, measurement. So of course, if you can do some kind of a neutron scattering experiment, then you get more information. But unfortunately, this is not possible here. Yeah.
if those layers supposed to have the finite filling, how can we do the layer resolvent?
Oh no. So in this case, carriers reside just in one layer, right?
Yeah, but for example, the lattice, there can be both finite fillings and done for those layer result question.
Because, so let's say, so let me come back here. So the transition we're looking at is from here to here. Or if the other layer will be looking at this transition. So they are at different colors. So you can look at different layers this way. That's the selectivity I was talking. You okay? This is the same material, the K and the K prime. Okay, so you brought up this long range interaction, and this actually is important because the lattice is 8 nanometer, and the size of the 1 year orbital is 2 nanometers. So they are same order of magnitude. So this V can be a significant portion of U. So we can't ignore them. So we can put back this long range interaction. So what does this long range interaction does? In addition of pulling, not allowing charges to occupy the same site, this long range will push them further away from each other, basically. So we need a experimental probe to see, what happens. And I already described one technique yesterday, the optically detected resistance and capacitance, right? So today I'm going to show a different technique to look at this. And this again is based on optics. So let me just walk you through some of the basics. So what we are looking at here is this monolayer tungsten sulfide or tungsten selenide, or one of those monolayers. And it has, effectively much reduced the dielectric function if you put this either in vacuum or embed this in boron nitride, because boron nitride has much smaller dielectric function than the semiconductor itself. So if we optically excite this, we have electron in a hole, and because of this reduced the dielectric screening, the interaction here is very strong. So the exciton binding energy, which is the difference between the fundamental exciton to the band edge, so this can be half electron volts, so something huge. And from early studies, we also know that you can detect series of those exciton states, like in atomic system, like second, third, whatever this exciton states. And then they have different Bohr radius. So for the 1s state, this fundamental exciton, it's kind of a tightly bound, it's small. If you look at the 2s, 3s, they are much bigger. So the idea is that, now if I have a sample that's sort of close to this monolayer sensor, but they are not electronically coupled. So they are just say, let's, capacity, the Coulomb interaction, right? So in that case, I can imagine that if the sample is metallic, then it will screen the electron hole in the sensor layer. So in that case, I expect all the exciton states to become weaker and the energy will shift. So the exciton binding will be weaker in that case. So by just looking at how the exciton binding changes with, the state in my sample, I should be able to sort of probe what's going on. So this is a kind of a little bit of a hand waving picture. So, we can sense whether there's a metallic state or insulating states, but it has difficulty to tell exactly how large is the insulating gap size, this and that. But this is good enough as a first indication of insulating states. So let me just show you the experimental result. So this is how the measurement results look at. So let me walk you through what we are looking at, okay? So this x-axis is the gate voltage, which changes doping density in my sample. And the positive side means I put an electron in, and the negative, I'm putting a hole in. So the y-axis is the energy. So what I'm looking at is the refraction contrast, as what we talked about yesterday, at the frequency of 2s exciton. And I already mentioned 2s exciton is on the order of 5 to 6 nanometer, and my sensor is 1 or 2 nanometer away from my sample. So you see some enhancement, some kind of a very large signal, here, all those blue spots. It looks like a Christmas tree, but it contains a lot of information here. So for most of filling, you just have some kind of a flat thing, and a weak response. And just means, the background, for most of the filling factors, we just have some kind of metallic states. And that's expected because you dope your sample, it becomes metallic. So at the 0 gate, we have the sample, no doping density. So this is the largest gap you have in your material, right? And you see very strong 2s response. So this is the band gap of the material. And a filling equal to 1 is the same as we talk about this Mott insulator. At a filling equal to 2, that's the band insulator we're talking about. And those are the pictures. But then we have a bunch of insulating states at the fractional fillings, commensurate fractional fillings. Stronger ones were like 1/3, 2/3, this, so on and so forth. So with our collaborator, we performed Monte Carlo simulation, and those states actually give those generalized Wigner crystal states, and that's the pattern how they should look like. And then of course you can estimate the energy scale of those, by warming them up. But yeah, go ahead. Yes. Yeah.
So I just want to clarify because I think I didn't completely understand. The exciton
in which layer does it live? I mean.
Oh, exciton is somewhere,
So
you
have a
know,
faraway
nothing to
exciton
do
in
with
there,
your
you can
sample.
probe the sample.
Exactly. But, you know, I also want to mention that, you know, this experimental result is much more complicated than the simple picture I just provide you, right? And you see all those interesting features, right? So, you know, in some sense, your sample is part of your sensor is part of your system to study, right? So the exciton response actually, you know, not just the sensor and some dielectrical background. So, you know, if you want to fully understand what's going on, you probably need to treat everything as an entire system. But the purpose of this study is to identify those insulating states, and it served this purpose very well. It's very sensitive, and you can find, you know, series of those insulating states. Yeah. Yes. Yeah.
The classical Omega 1/3 and 2/3 would be particles.
Yeah. So you can see here they are slightly different, but not too different. And the reason is because, you know, in this case, U over T is very large. So this, you know, fluctuations do not matter that much.
How does the melting temperature compare on this?
Oh, melting temperature, yeah. We have a good agreement. So, yeah.
Light reflectance.
Yeah.
And then, is there any like reason, or maybe you did do this, like you did red reflectance, like an experimental challenge for that to look at like the Drude peak and how it evolves with filling?
Yeah. So the question is, you know, so this is all in the visible, right? Infrared is a little bit difficult because the spot size is very big, and for Drude, you know, we're talking about spot size 300 times bigger than your sample.
So if I just really take it ideally,
Yeah.
negative and positive gate voltage is corresponding to dot on the underneath is like black is like switched to the white, right?
So electron doping and hole doping.
Right.
Yeah.
So why they are not data doesn't look that symmetric? Why is that? Like especially when you go to the higher gate voltage.
Oh, yeah. Okay. So yeah. So the question is, you know, why this flat point that is not quite the same, you know. So yesterday I touched upon this issue of this multi-layer system, you know, the multiple refraction, you know, you have many layers, you know, the effective substrate question. So you can also see, you know, the spectrum doesn't just look like, you know, you have one absorption peak, another absorption peak, right? So here you have, if you look at the values, some negative and a positive, right? So this is all due to interference effect, you know, how you have, because your sample is living in some environment, you have multiple reflection. And this will also change, you know, when you change the doping or gate voltage, the environment changes a little bit. So it's not fully expected to have, you know, electron doping or hole doping, everything should look perfect.
But in principle, it should. I mean, if you have a parabola band up and down.
So
like as you draw over there.
Yeah. So the conduction band and the valence band are also a little bit different in these materials. Yeah, so they are not quite the same. And you can also see, you know, like one side you have more insulating states than the other side, maybe, you know, the strength also a little bit different. So this is also expected because the band dispersion for the conduction band and valence band. Yeah.
So in principle, that, you know, like for example, the gate voltage is like 5, that look like near the very dark insulating state at the center, and then it has some kind of dispersion looking kind of.
Oh yes.
thing. So
Yeah.
where did that come from?
Yeah. So this is something actually pretty well understood because let me do here. Maybe I just explain in words. So let's say, we have a piece of a doped semiconductor, or we first start with some intrinsic semiconductor, and you do optical absorption measurements, right? And we see this very strong exciton resonance. Now we are going to introduce charge into this material, right? So how do we model this, So you can think of this like some kind of boronic thing, But if you measure the absorption of the exciton, when you introduce doping, it doesn't disappear immediately. So you can weaken it, and then, other branches will coming out of this, at some point you even get a trion, 3 particle bound states, things like that. So this is something, it's the doping dependence of your exciton absorption. Okay, so now if we look at, for example, filling 1/2, it breaks rotation symmetry, right? You can see this immediately. So can we also see this in experiment? And the answer is yes, using the technique I talked about yesterday by following the polarization, So if you look at this, this direction and that direction definitely is different. So if you have a sensitive optical anisotropy measurement, you will pick up this birefringence. And you can also determine the direction of this linear chain. And you can map out, in your sample, you have domains, chain along this way and that way, and that can also be done. So I just want to show you kind of the phase diagram. So what this shows is the strength of the anisotropy, the rotation symmetry is broken. And we saw that at filling equal to half, the linear chain, definitely breaks that. And that's this thing, has a very strong signal. At 2/5 or 3/5, it also breaks rotation symmetry, and it can also be picked up. But it's not just at those fillings, we break a rotation symmetry. And this experiment shows that, it breaks rotation symmetry over a wide range of doping density. And it finishes somewhere at 1/3 on one side and 2/3 on the other side. And when you warm the sample up, they disappear gradually. So the strongest stripe phase actually is at filling half. And this perhaps will give, you guys something to think about, what are the nature of the stripe phases, whether you have some kind of a parent stripe phase, some pneumatic, some intermediate thing, and then eventually you come down to crystal. So that's something to think about. Yeah.
So they were sweet, black, white.
Oh, so outside there's no signal, so they are not. Yeah. So that means, those are the Maury lattice, and the black means we have holes there. The white means it's unoccupied. Sorry, I should have made it clear. Yeah. Oh, okay. This is very schematic. You remember from previous slide, so in the strong U/T limit, there's proposal that for triangular lattice, the ground state could be 120-degree Neal ordered antiferromagnet. But this is not something we observe in experiment. So this is a question mark. Potentially, this could be the ground state.
Do you also see the anisotrope in the transport?
So unfortunately, in those early experiments, we cannot measure those things in transport.
Rotation symmetry broken phase dome that
Yeah.
not all of them are in state. Some of them are.
Some are metallic. Yes. Yeah. And this is a very relatively small signal. And, you know, I think for transport, the tricky thing is the domain size. So the domain size, I don't have data to show here. Domain size is like micron, a few micron. So if you have a transport device, you know, usually you have quite a few different domains. So I'm not sure you'll be able to pick up some preferred direction.
So the mechanic state you have.
Yeah. Yeah.
What do they look like? It's like the momentum space is like a Fermi surface that is not a circle. Is that
I don't know. Yeah, so that's something needs to think about. It's possible, you know, you have some kind of liquid crystalline like state. Okay. So I talk about the limit when U over T is big, right? Then you may ask a question, you know, can you study the transition? Can you continuously tune the U over T limit? So large U over T, you know, we have mod insulator. If we tune the U over T, you know, at some point you'll get to the metallic state. So this gives us, you know, opportunity to continuously tune this parameter, U over T, and to look at this transition. Is this first order as Mott initially thought, or this could be continuous phase transition? So we need to pick up some system to do this. So the first example I showed, you know, you have very large U over T, you can't do too much. So we picked this combination. In this case, you know, the lattice mismatch is bigger, 7%, and that makes the lattice constant smaller. So we start with a little bit bigger T. And then what's kind of interesting is that we have this displacement field, and this displacement field can tune the Moray potential depth. And if you can do that, you can change T significantly. So by this knob, the electric field, vertical electric field, we can tune the T over U or U over T. So this is an experiment. So now we measure the resistance at the filling equal to 1, it's fixed. And what we are changing is just the vertical displacement field. So for small displacement field, you know, we have this insulating behavior. And for large displacement field, it becomes metallic. And if you look at down here, you know, this follows T square. So it's a good Fermi liquid. And you can do scaling, you know, you can scale this into 2 groups, the insulating and the metallic. And you can also do the capacitance measurement, measure the size of this gap as function of displacement field. And you can also fit this, you know, find the A coefficient to see how it changes with the tuning parameter, which is the displacement field, and put everything together. So on the insulating side, the charge gap decreases when we approach the metal to insulator to metal transition. So, you know, roughly till this point, it looks like still going down. But, you know, of course, in the experiment, there's always disorder. So it's close to the transition, but, you know, looks like it continues going down to 0. On the other hand, if you look at this Fermi liquid behavior on the metallic side, the A coefficient diverges, but then still there's the question, you know, it's not quite at this point, right? So based on this data, it looks like we have kind of continuous phase transition, you know, up to this disorder density, yeah. Yeah, this is from capacitance.
Would we expect dielectric breakdown?
So I understand what you're talking about, this dielectric catastrophe, but I don't know how this will reflect on this measurement. We can chat a little bit more. Yeah. Okay. So this is by looking at the transport measurement, and you can look at the magnetic susceptibility. It looks like from this side, the local moments character changes to some Pauli. It's because of Fermi liquid, but the magnetic stability changes from one side to the other side smoothly. And even when we measure down to temperature, which is about 5% of the Curie-Weiss temperature. So this data shows that there's no sign of spin gap or some long-range magnetic ordering. And if we just come back to this, but from the charge transport measurement, it looks like some kind of a continuous small transition. So then the question is, how do we describe something like this? Fermi gap vanishes, suddenly across this. I think Shan II has some theory of. I don't have here. Did he talk about this? No. Okay, so I think this is also an interesting theoretical question to think about, some kind of a continuous Moore transition. How do we describe something like that?
So can I think about that x-axis as a number of carriers?
Oh, no. Number of carriers is fixed. It's always at 1. So what this axis, it's the vertical displacement field. So what this is doing is changing the bandwidth. So the doping density is fixed at 1. And from this side, it's a Mott insulator. This side is Fermi liquid. So when we tune the displacement field.
So how can I understand that? I try to understand, so that susceptibility should come from the like spin-spin interaction, or is that some temperature independent Pauli? How should I understand?
Yeah, so on the left-hand side, when we have the Mott insulator, and this is the super exchange I talk about. Yeah, and on the other side, it's the Pauli magnetic susceptibility. It's liquid. So the point I want to show here is that there is no jump or anything. It looks like susceptibility smoothly changes from one side to the other. So the charge seems that charge gap closes abruptly at this point, but from magnetic aspect, there's no sign of spin gap or some long range magnetic order. Yeah, that's what.
Part, but
yeah.
Now in the right-hand side,
Yeah.
Pauli paramagnetic susceptibilities should be proportional to density of state, roughly. And how can I understand bandwidth change? How bandwidth change that density of state is changing? I mean, so that actually decreasing down, right? I mean,
Yeah. Oh,
so
you mean this?
Yeah, so that's why I'm asking what x-axis will corresponding to. I mean, so.
Yeah. So
if you have so bandwidth is like getting larger as you go farther.
yes.
So how does it affecting the Pauli paramagnetism? I actually don't know how to think about this.
So maybe will be something for you guys to think about this for Fermi liquid when you increase the bandwidth, how the Pauli magnetic susceptibility should change with bandwidth. So I'll put a question mark here. Okay. Oh, okay. So this is a paper I was talking about, some argument of, whether there should be quantum spin liquids, but that's beyond me.
By any chance, did you get how the susceptibility deep in the model?
I think this is all the data we have. You mean, like how this side will. Yeah, I think unfortunately, this is all what we have. Yeah.
If you compare the polysys, the
Yeah.
coefficient of the t squared and semi-liquid.
Yeah.
Could you like you compare them and see? I mean, if one is density of t squared and the other one is linear density.
So you're talking about this coefficient, right? Yeah.
This is m star and the other one should be n.
Yeah. So I think back to the data, maybe roughly they're okay, but those two are also from two different devices. So the axis scale is a little bit different.
Downward trend.
Yeah,
It must
yeah.
be
It could be that this is just sharper because it's m squared.
M square.
less.
Yeah. So this, yeah. Okay. That's a good point.
If you are to set a value of U over T, increase of the temperature, you melt the more insulator into something, right?
Yeah.
What is the melted?
So it's your question of whether it's fermi-liquid or it's not fermi-liquid, right? It's fermi-liquid, and I should point out there's one kind of a subtlety here, So we sort of treat it as a triangular Hubble model, but in the Moray there are multiple. The thing I want to point out that the temperature scale is not necessarily the U scale, because here it could be charge transfer insulator because there are other Moray lattice sites. So this temperature scale actually gives us something smaller than U. It's not quite the U. Okay, so how much time do I have? 7 minutes. Maybe I should. Do you have questions? Should I discuss another system, or I can just stop? What's your?
I think we can start a little.
Okay. Okay. So I showed you a system that we apply a large displacement field, we can sort of tune U over T, but it's kind of limited. And I mentioned that with homobilayer, actually you have a large tunability, by changing the twisting angle. So I want to introduce this homobilayer, and you probably have seen this from Alan's talk, right? And for constant solenoid, actually, for small twist angle, this is the current understanding, and the picture may change, when more numerical data become available. So they can occupy a different lattice sites. So in the small twist angle case, they occupy the MXXM, and this can give you topological bands. But for large twist angle, they can occupy this AA metal on metal sites. And this can be just modeled as a simple triangular lattice Hubble model. So we're going to look at this case a little bit. For monolayer, so you can think about, the bands from the two layers are hybridized. So if we look at the K and the K plus the K minus points in the Moray mini Brillouin zone, so the bands actually come from one layer, and this bands, for example, is dominated by layer 1, and this bands at this point is dominated by layer 2, and you can look at it from this projection. So they hybridize and then open up a gap here. So this is the hybridization gap. So this is a case with the two layers at the same potential, but if you apply a displacement field, you sort of make them at different potential. So in this case, you have the two spins from two different layers, they are degenerate. But now if you apply displacement field, they become spin split. So then if you write down the Hamiltonian, the hopping will be dependent on the spin states. So you can introduce a term, something like a spin orbital coupling. So this displacement field will change both the amplitude of the hopping, but not too much. So this is from numerical studies, but it will significantly change the spin orbit term. So this will be the modified triangular Hubble model for example, twisted tungsten sulfide selenide when the twisted angle is big. We are not in the topological regime. And then you say, what is the correlated insulating? So, at the filling equal to 1 in a large U over T limit, and you can sort of rework out, this Hamiltonian to get this simple, spin model. So you have this phi, which is the measure of the displacement field here. So like two terms, XXZ model and also, Zelenshansky-Maria interaction here. So when there is no displacement field, you just go back to the triangular lattice Heisenberg model. And there are some arguments possible with quantum spin liquids. But then at high displacement field, as we study here, it's anisotropic. And, this state is kind of preferred. So that's from those models. So we can look at the experiments, so in experiments, so we look at the different twist angle. And one thing you can see very clearly, so let me just explain this plot. So the x-axis is the doping density, and y-axis is the displacement field. So you sort of see some kind of a triangular area here. And this is the area when the two layers are hybridized. And if you apply too large displacement fields, they decouple. So the interesting thing happens, inside this triangular area. And you see those very red or black-like features, and that means very large resistance. Those are the insulating states. And kind of interesting, like a small twist angle, you have a very insulating states. And then when you go to large twist angle, insulating states already gone. So this just shows that, when we twist the angle, the U over W is smaller. So the bandwidth becomes bigger and bigger. And what's interesting is that, in this system, from earlier studies, one from our group, one from Columbia group, around this twisted angle, when we cool down the sample, we find a superconductivity somewhere here near the Mott transition. And in the data of Columbia group, there's no more insulating state. And they find the superconductivity somewhere close to filling 1, but a little bit away. But when it's close to Van Hoff singularity, and it's connected to some kind of an antiferromagnetic metal. So we believe that there will be a superconductivity, in the whole range. And this twist angle gives us this knob to find the regime when U over W comparable, when you are close to Mott transition. And this is the idea to see whether we can, see something similar to what the high TC materials will show. So maybe I just flash some results and then.
Right, in 1 or 2 minutes.
Yeah. So indeed, we find superconductivity. And then if you zoomed into this superconducting regime here, so you have some kind of insulating state, doped insulating state, and then you have this superconductor wrapped around it. And the highest TC actually occurs right at the boundary when you have the Mott transition. And we also know the nature of this this insulating state, by doing magnetic stability measurement. Now it shows this neo transition, and we can probe the neo temperature. So I don't have time to walk you through, but so basically by doing the transport and the magnetic stability measurement, we can map out this whole phase diagram. So let me just show maybe 1 or 2 plots. So those are just different cuts at different displacement field, when you also vary the bandwidth. So this is the antiferromagnetic insulator. And when you dope it, it has small Fermi surface. So this is a metallic but small Fermi surface. And then at the edge, the superconducting dome emerges. And outside, you have a large Fermi surface. So small Fermi surface, what I mean is like a counted from filling equal to 1. Right? And that's from the whole measurements. And then at further doping, you get a Fermi liquid. So, something like this, surely reminds you of the high TC phase diagram. But, exactly what's going on here, whether you have, and we also see linear resistivity, so I'm not going to get into the details. So the bottom line is that, by tuning the system close to Mach transition and probe here this Mach insulator, there is superconductivity and superconducting domes, and the behavior is very similar to what high TC materials demonstrate. So whether this superconductivity, comes out from doped Mach insulator, I think this is a question that we can revisit using this highly controlled system. So I should finish. So this is just a schematic of phase diagram, right? We change filling, we change bandwidth. At the filling equal to 1, we have Mach insulator, and we have some kind of continuous Mach transition. And we have a bunch of those generalized crystal states, and some of them has broken rotation symmetry. And if you look at the tip of this, superconductor emerges, and it has complicated phase diagram. So I think, this system is quite rich and requires further both experimental and theoretical investigation. So this is pretty much I want to say. Sorry, I don't have time to talk about, the topological properties. If you guys like, I can talk about topological properties, or I can talk about what, I plan to talk, this electron hole double layer, maybe quick thing. What do you prefer? Okay. Okay. Yeah, so I'm done for today.
So in the experiment of the diagram, right, so there are some black dots. They are black dots.
Black dots? Oh, you mean those? Oh, okay. Okay, so those are the temperature we map out, so those are the new temperature we measured, so, and then, so this is the coherent for Fermi liquid, those blue dots. And this is something we don't quite understand. If we look at the resistance as a function of the temperature, we have linear dependence, and at some point, below it becomes sublinear. I think this has also sublinear. It's so linear and a force below the linear dependence, sublinear. That's what I mean.
Due to some higher power.
Lower power,
Lower.
sublinear.
Do you have any indication of how this, like, is this power roughly the same or does it vary?
Hard to tell.
So what did you do to check this is like superconductivity? Just literally taking your data that
Ah.
resistance is like at the 10 ohm. And I mean, according to the color bar, I mean, just that's
Okay.
book scale.
Yeah.
But what kind of thing
Yeah.
have you checked?
Okay,
whether that
here,
is
this is an excellent point. So I don't have the data here, but I can tell you, what we did. So, so for example, we look at the, of course, temperature dependence actually goes down to 0 at some temperature. We look at the magnetic field dependence, and we can extract coherent lengths, all those things, and look at the current dependence. There's a superconducting critical current. So all those things have been checked. But of course, it will be the follow-up studies. We need to measure. For example, build some junctions. So look at this superconductivity more carefully.
So like, can you tell us what will be the roughly critical field of this superconductivity?
Oh, relatively low.
So like 100 Gauss or?
So 50 millitesla, something like that. Yeah.
1.5 millitesla.
50.
Oh, 50
50. Yeah. So
So compared to the small twist angle device that you first reported, the superconductivity, which appeared as 0 electric field.
Yeah.
What happened between the atoms? Like the superconducting regime separated as a function of this angle, or?
Okay, so I think so. Actually, this spot is superconducting, but at the 0 field, we have not observed the 0 resistance. Although you see it's dropping, but experimentally, it's not a superconductor yet. So it may not be.
Then the superconductivity appears between the intermediate angles and 3 of.
No. This is not what I mean. So you can see this, insulator superconductor, right? When you increase the angle, this thing opens up, right? And then the superconductor will be here, right? Around this point. And then when you open up more, so this is like wrapping around here. So the insulator moves out. And then eventually, when the bandwidth is large enough, insulator is totally gone. And then, you see something like here. Yeah, so this.
And the linear and peak resistance. I mean, like, what's the residual resistivity?
Very small.
Very small.
Yeah.
One last question. Go ahead.
Which measurements do you use to identify TC? This is also like a really non.
It's a BKT
The
temperature.
temperature.
Yeah.
Okay, let's stay here.